Hello friends, today we will learn architecture of 8086 microprocessor. In the last lecture we have studied part of 8086 architecture. The remaining part will be conducted in this lecture. This is the block diagram. What we have studied in the last lecture, we'll just revise it one more time. With this microprocessor architecture, what we have studied is memory is connected to this microprocessor. This particular part is known as bus interface unit. This particular part is known as bus interface unit, with which we will get all the information from memory. We'll get all the information from memory to microprocessor. With this particular instruction bytes will store all these information in these bytes, are known as a Q data structure. Then this information is further communicated to arithmetic logical unit and these registers. These registers are nothing but the general purpose registers. The general purpose registers are 16-bit in size. So the information stored will be used for arithmetic and logical units, and then this information will reflect the result into the flags. So whatever is the result of arithmetic and logical unit instructions, the results will be reflected to the flags. Then the registers like SP, BP, SI, DI are special purpose registers. These are used for special purpose. All these are 16-bit registers. AX, BX, CX, DX are 16-bit registers, whereas these can also be used as 8-bit registers known as AH, AL, BH, BL, CH, CL and DH, DL. This particular unit is known as execution unit. We have two parts in 8086 block diagram. One is BIU, bus interface unit, with which we'll get the information in an execution unit where the instruction or the processing will be done. So that's why we call this as a execution unit. So the ES, CS, SS, DS, these are known as segment registers. These segment register will hold the address of the segments which are available in microprocessor. If this is a memory, then this is a code segment register, then the starting address of this will be held in code segment register, whereas the starting address of extra segment register will be stored in ES, same as CS and DS, stack segment and data segment registers. This all we have studied in the last lecture. As I said, we'll just revise few things as a extra segment, code segment, stack segment and data segment registers. These segment register will hold the starting address of the segments. Segment is nothing but a parts. 16 kilobyte part. If this is a 1 megabyte of memory, then the remaining part, the memory is divided in number of parts. So each part is known as a segment. The starting address of each part will be stored in the respective segment registers. These are registers. These are nothing but a 16-bit in size. 16-bit in size. And we store the starting address of these registers into these segment registers. Why we store these in segment registers? Because we need to find out the starting location of those segment registers. Once we find out the starting address of the segment register, then we can eventually make use of the further locations in that particular segment for storing the information. Then we have a 16-bit instruction pointer. This 16-bit instruction pointer is used to point the instruction, the next instruction to be executed in code segment. What we do? we will store the program that to be executed in code segment, will access it one after another, and that will be always pointed with instruction pointer register. So this will be done. Then we have also studied some of the general purpose register. As we said, AX, BX, CX, DX. The AX is always known as accumulator, BX is known as base register, CX is always used for counter. When we use a loop, then we have a counter, and this is always by default this is known as a counter. Instead of counter, we also can make use of this CX for a general purpose register. Then we have data register. Then this is SP is a stack pointer used for stack related operations. This is used for base register, base pointer, then source index and destination index. These two registers are used for copying a data or moving a data from one place to another place. In this purpose, we have few defined instructions, and at that situation we have source index and destination index register. Then we have flag register. The result of the arithmetic and logical unit will be reflected into the flag registers. It will show what has happened during the execution, and that results into flag register, which helps us to understand what is the result of arithmetic and logical unit. Then, as I said, the stack pointer, base pointer, source index and destination index and instruction pointer are used as a 16-bit registers only. No higher and lower register can be accessible in these registers. Whereas instruction pointer is not directly accessible to the programmer, it can be used by the machine itself. So instruction pointer will always point to the next instruction to be executed by the microprocessor. Now today we will learn the flag registers. So first of all, flag register is a 16-bit register. Flag register is a 16-bit register. Few points, it starts from here 0 to 15. Few are which are undefined. Few bits are undefined. So these undefined bits are not used, whereas the defined bits are used either 0 or 1 on that particular location. This is the overflow flag, known as this is the overflow flag. Then we have a direction flag. Then this is a interrupt enable flag. Then we have a trap flag. Next is a sign flag. Then next, this is ZF, means 0 flag. Then we have auxiliary carry flag. Then the next is parity flag, and the last is a carry flag. So these are few flags, out of which 6 are known as status flag and 3 are known as control flag. Status flag means we can understand the status of microprocessor or status of the result what has been generated, whereas 3 control flags are allowed the program during the program that can be set or reset, with which we can control the processing. That's why we call these 3 flags as a control flags, whereas 6 flags are known as a status flags. We can understand, again I repeat, the flag register is a 16-bit wide. This will reflect the results after the result of arithmetic and logical unit. Generally, the result will be stored in the arithmetic accumulator, means AX register. So let's see that this is a 8-bit register. This is a lower nibble 0, 1, 2 and 3. The first 4 bit are known as lower nibble. Upper 4 bit are known as upper nibble. This total is 8 bit, means 1 byte information is available. If we add 1 byte of data into another 1 byte of data, then some result will be generated after addition. And after addition, we will get a carry will be generated. So if a carry is generated, then we'll set a carry flag on. The carry flag will be set, it will be on. If we add and the carry, let's say this is 0 1 1, then 1 plus 0 0, 0 0 is 0, and then 1 plus 1 is 0, but a carry is generated here. So this carry from lower nibble to upper nibble is generated. This is known as auxiliary carry flag. This is known as auxiliary carry flag. The same is with parity. If it depends on how many number of even or odd number of ones available after generation of result, depending on that parity flag will be set. So this is how the flags will be generated. Now what we said just now, we understood the result of the total 8-bit is done, and if the carry is generated after addition, then a carry flag will be set. The parity flag, if this flag will be set if lower byte of the result contains even number of ones. If 2 number of ones are there, then flag will be set. If 4 number of ones are there, then flag will be set. Set means 1. It will be set means 1 will appear into this parity flag. If odd number of ones are there, it will be set to 0. Then the next is auxiliary carry flag. In auxiliary carry flag, if the lower nibble generates a carry to a upper nibble, then auxiliary carry flag will be set. Otherwise it will be reset, it will be 0. Then the next is we have 0 flag. If the result of addition, subtraction, whatever will be 0, then this 0 flag will be set. It will say that the result of operation is 0. Then we have a sign flag. So this sign flag will be set if the result of operation is negative. If the result of operation is negative, then this sign flag will be set. Then we have a trap flag. So this is a control flag. This flag is set when the processor enters into single step execution mode. Single step execution means we are about to execute the complete program one after another, line by line. Many times we'll execute the program completely. Once we'll say execute, it will start executing from first line to last line. But sometimes we want to execute the program one after another. So this is known as single step execution. So during the single step execution, this flag will be set. Then we have a interrupt flag. 8086 recognizes the external mask interrupts. Clearing IF enables these interrupts. When we set an interrupt flag, then outside interrupts means somebody is requesting for service. Somebody means the devices are expecting to have a service from microprocessor. So when a device is expecting a service, it will generate the interrupt. Interrupt means it will call, it will request the microprocessor, please provide me the service. So this can be interrupted, this can be avoided by the microprocessor by setting the flag on. Then we have next is direction flag. The direction flag is, this flag is set when we want the processing of the strings. The string is processed beginning from the lowest address to the highest address. It is auto increment mode. Let's say that if we are working on 2 strings, or when we are copying a data from one place to another place, then we will have few instructions which will execute automatically. During that, if we set this direction flag on, then it will work in a reverse direction from highest address to lower address. But if this flag is set 0, then auto increment from lower to higher, it will be automatically incremented and data will be copied from one location to another location. Then we have overflow flag. So in this overflow flag, if the result of operation is more than the available data size, then this flag will be set. It is like a 8-bit operation. If it is 8-bit operation and the result is more than that, then overflow flag will be set and the remaining data will be stored in some other register. So this is how overflow flag is used. Then we need to understand the stack operation. Stack is one type of data structure. So this data structure is used maximum in the process of subroutine call, or we can say that a function call. If a main program is being executed one after another and then some function is being called and then the processor switch to that particular location and then the function will be executed. After execution of this function, then again the microprocessor come to the location from where it left and start executing the remaining part of the program. So if we say that this is a main program and this is a subroutine, then this stack will be used in this particular location. Let us assume this is a stack, and what we do, we will have a location. When the main program is being executed, then the address, the location of this particular program has to be stored. This has to be stored here. This is known as program environment. And then the processor switch on to the particular function for execution. As it has left the previous location, this location has to be recalled. That's why we will store it into the stack and then we'll move back to the function. After execution of this particular function, then the processor has to come back to the previous location. So this can be done with the stack pop. Get the previous location back into the microprocessor and start executing from this particular location from it left. That's where we can make use of the stack very efficiently. So for microprocessor, what we say, the stack is used for temporary storage of information such as data or addresses. So whatever information, we'll say that program status word or program information. So this program information will be stored in a stack. Whenever a call is executed, so in microprocessor 8086 there is a instruction known as call. So this call, whenever this call is being executed, then the function will be called. So the microprocessor 8086 has to switch to the function. It has to switch to the function. So before that, it will execute a push function. It will push the contents of current execution here into the stack. Then it will execute the particular function and then come back to the previous location. This is known as stack. CS and IP will understand what is CS and IP. CSC, this is a microprocessor. So this is a memory, and we have CS. This is a control segment. This is a control segment register, and this control segment segment has a starting address as a CS control segment. So this control segment and instruction pointer is always pointing to the instruction in the control segment, because control segment has got the program instruction. So set of instruction is known as a program. So this set of instructions are being executed one after another by instruction pointer. So code segment will hold, this code segment will hold the starting address of code segment, whereas instruction pointer will hold the address of this particular instruction which is to be executed next. So whenever a function main program is being called, then CS and IP are same. But when a program is being called, a function is being called, so this function, when the function is being called, then the CS and IP has to be stored here, and then it will move to the new CS and IP, where the program is, the function is stored. This function is stored here, and the main program is stored here. When the function is executed, it has to move to a new CS and IP or new function. Once the function is executed, then it has to come back to the previous location. So for that, the pop operation will be done, and then the remaining function will be executed. This is how it works. The registers, other register can also be pushed before return from the subroutine. Pop instructions can be used. The pop values can be back from the stack into the corresponding registers. This is how stack work. Now this is what the stack pointer and stack segment is. As I said, stack segment, this is nothing but a memory. This is a memory. So in this memory we have got a stack. So this is a end of the stack. This is a 0 0 0 0. Let's assume 0 0 is a end of a stack, and this is a bottom of the stack. Say F F F F F H. This is the top of the stack. This is how we push the contents. We keep pushing the contents here one after another, and whenever we want, we pop out the contents. What is stored? This stack segment will hold the bottom of the stack, and it will keep as it is, same. The same contents will be there always. When we will have the stack pointer, then the stack pointer will be incrementing and decrementing as per the requirement, because stack pointer will always point the topmost value on the stack, and this is how it works. We have already studied the stack, and the same way it works here. I hope you understood many things related with the remaining part of this 8086 architecture. In the next lecture, we will work on, or will study, the pin diagram of microprocessor 8086. Thank you.